Now, in our previous lecture we have defined the uniform approximation. Let us briefly review what we have done last time. We considered the linear polynomial approximation. So, let us write it as a uniform approximation. And then to define this we consider a linear polynomial approximation. We have taken this linear polynomial approximation as p1 x is equal to some c naught plus c1 into x. Then we have defined the error. The error is defined as epsilon of x, that is f x minus p1 x, that is f x minus c naught plus c1 x. Now, the problem of uniform approximation therefore is that the maximum of error should be equal to the minimum error in the interval, whatever the interval we have considered a b. That means, maximum of the error in the interval a less than x less than or equal to b of this magnitude should be equal to minimum of a less than x less than or equal to b of error x. This would imply that the error, all the errors are equal in magnitude, because the maximum should be equal to the minimum. Therefore, the errors at all the points would be identically same, and that is got magnitude of epsilon of x. Now, for considering the linear polynomial approximation, we will take 3 points x1, x2, x3. So, take 3 points, we will take the first point as x1, the second point as x2, and the third point as x3, x3 is equal to b. If we define the largest value of epsilon x in magnitude as E1, let us define E1 as maximum of a less than x less than or equal to b in magnitude of epsilon x. Then uniform approximation would mean that the error at these points epsilon xi, that is equal to f at xi minus c0. I am substituting x is equal to xi in this equation. So, c1 of xi they would be equal to either with a plus sign or with a negative sign of E1. E1 is the maximum magnitude, therefore, they would be having plus minus signs. That means, we require that epsilon xi alternate in sign. It may start with plus E1, then it become minus E1 and then plus E1, or it may start with minus E1, then it may go to plus E1 and minus E1. For example, in the simple case of a example of a graph of the error like this, looking like this, if I take this line as this, then I will take this as x1, this as x3, and this is my E1, and this is minus E1, and this is equal to E1. Now, I have not yet numbered this, I will just number it. Now, since the error here of the graph is this is E1, this is E1, therefore, I can apply the Rolle's theorem immediately on the error function. So, we have by Rolle's theorem epsilon dash x, derivative of epsilon x is equal to 0 at some point in a b. This is x3 is equal to b, a is equal to x1 between some point, and we take this point is as x2. So, we will take this point as x2, let this point be x2. In other words, we are setting epsilon dash x2 is equal to 0. So, the x2 satisfies this equation epsilon dash x2 is equal to 0. Now, I have got 3 equations. let me repeat this equation here. So, let us take I is equal to 1 and 2 from here. So, this first equation reads, put x I is equal to 1, x 1 is equal to minus epsilon x 2, they should alternate in sign. Error at the next point will be opposite sign of the error at the next point. Of course, you can view this as epsilon x 1 plus epsilon x 2 is 0, epsilon x 2 plus epsilon x 3 is equal to 0, and the third equation is derivative at x 2 is equal to 0. Now, the quantities that we have to determine in our approximation are C naught is to be determined, C 1 is to be determined, x 2 is unknown. So, I need to determine C naught, C 1 and x 2. Therefore, I have got 3 equations in 3 unknowns. Therefore, these are 3 equations in 3 unknowns. Now, we can solve this, however, this is going to be nonlinear equations. However, there is a simple way of solving them, because this equation is going to be simpler than this, but if you look at these first 2 equations, interestingly it will be epsilon x 1 is equal to minus epsilon x 2, continue the next equation, this is epsilon x 3. I just combine the 2 equations. Now, if I take these 2 as an equation coming out of this for solving, gives you an interesting equation which simplifies and obtains the solution of one of the parameters immediately, and that will give you substitution backwards, and then you can obtain the solution of the problem. Now, let us look at how we are going to do this in this problem. Now, our polynomial is epsilon x is equal to this. I am substituting epsilon x 1, that is x 1 is equal to a. So, that is f at a minus C naught plus C 1 at a. So, I will let us take it as f at a minus C naught minus C 1 at a, that is this. On the right hand side, I have epsilon at x 2. So, this will be f of x 2 minus C naught minus C 1 x 2. The second equation reads f at x 2 minus C naught minus C 1 x 2, this is epsilon at x 3, x 3 is equal to b. So, I will set f at b minus C 1 minus C 1 of b. Now, I differentiate epsilon. So, if I differentiate, I will get f dash at x 2 derivative of C naught plus C 1 x. So, I will have simply C 1 is equal to 0. Now, I need to solve these 3 equations. Let us use this equation, that is I subtract these 2 equations. So, let us number it as 1, 2 and 3. I take it to this side and then write it as add it. I can take it as addition of these 2 equations or as equating these 2 equations. That will then give me f of a minus C naught minus C 1 a is equal to f of b minus C naught minus C 1 of b. That is epsilon x 1 is equal to epsilon x 2. Now, here I can see that C naught cancels with C naught. So, I can bring this C 1 b to this side and then solve for C 1. Therefore, I can have C 1 of b minus a is f of b minus f of a. Therefore, solution of C 1 is obtained, f of b minus f of a divided by b minus of a. Now, when once I get C 1 from here, equation 3 gives me x 2. Now, equation 3 determines x 2. When once C 1 and x 2 are determined, I can use any one of the equations 1 or 2 to find out x 1. So, we use 1 or 2 to find C naught. And that completes the determination of the polynomial, and we can also find out what is the maximum error. I can take any one of the points and find out the error, because the error is in magnitude is the same. So, I can use the first point or the last point or any point to find out what will be the uniform error here in this particular case. Now, let us take an example for this to see how we are going to use this. So, we shall use the same example which we have done in the least square approximation, so that we can have a comparison. So, find the Chebyshev linear polynomial approximation, which is same as the uniform approximation. To the function, let us take the same function which we have done earlier, f x is equal to x cubed on 0 1. Now, as we have done just now, let us take the required approximation p 1 x is equal to c naught plus c 1 x and define our error as epsilon x is equal to x cubed minus c naught plus c 1 x. Now, I need to choose 3 points in the interval 0 to 1, including the end points. So, I choose the 3 points as x 0 x 1 is equal to 0, x 2 is x 2, x 3 is equal to 1. Now, the first equation reads epsilon at x 1 is equal to minus epsilon at x 2. Now, let us substitute x 1 is equal to 0. So, this gives us 0, this is 0, therefore, I will have minus c naught from here, and that is equal to minus epsilon at x 2, that is x 2 cubed minus c naught minus c 1 x 2. The second equation reads epsilon x 2 is minus epsilon x 3. So, let us substitute x 2 cubed minus c naught minus c 1 x 2, and the right hand side this is plus, we will take this, and minus epsilon x 3. Now, x 3 is equal to 1. So, I will substitute x is equal to 1 in this, that is 1 minus c naught plus c 1. Add these two first and then solve it and then write the third equation afterwards. So, I add these two. So, I will therefore have minus c naught. Now, I am adding these two. So, these two have cancelled. So, I am going to, or we are looking at writing the third equation as epsilon x 1 is equal to epsilon x 3, that is epsilon at 0 is equal to epsilon at 1. So, that is what we are mean by adding these two equations. So, this is epsilon at 0, that gives you epsilon at 0 gives us minus c 0. So, that is what we have here, and epsilon at 1 is equal to this quantity, therefore, this gives you 1 minus c naught minus c 1. C naught cancels, I will get c 1 is equal to 1. So, the value of c 1 is equal to 1. Now, I will write the third equation epsilon dash at x 2 is equal to 0. Now, I differentiate my epsilon x. that is 3x squared minus C 1, 3x squared minus C 1, and this should be equal to 0. C 1 is 1. So, let us take it to this side and write x 2 is x 2 squared is 1 upon 3, x 2 is equal to plus minus 1 upon root 3, but we are in the interval 0 to 1. Therefore, I can throw away the value minus 1 upon root 3. Therefore, the required value of x 2 is 1 upon root 3. Now, I can use any one of these equations to get my value of C naught. So, let us take the first equation and write it. Let us just rewrite this equation here. This is minus C naught is minus x 2 cubed plus C naught plus C 1 x 2. So, if I take it to this side, I will have here 2 C naught and bring it to this side x 2 cubed minus C 1 x 2. And x 2 cube, let us take the cube of this, that is 1 upon 3 root 3 minus 1 upon root 3, x 2 is C 1 is equal to 1. Therefore, this is minus 2 upon 3 root 3. Therefore, C naught is equal to minus 1 upon 3 root 3, or we write this as root 3 by 9. Therefore, P 1 x, the required polynomial, is minus root 3 by 9 and C 1 is equal to 1, that is equal to x. Now, let us just see whether what we have started with and what is uniform approximation is really satisfied by this. Just as a, let us have it as a check, let us call it as a check. So, our error is x cubed minus x minus root 3 by 9, C naught plus C 1 x we have substituted. Let us get the error at 0, error at 0 is root 3 by 9, substitute x is 0. Now, let us go to the last point epsilon at 1, that is 1 minus 1 plus root 3 by 9, that is equal to root 3 by 9. Then the x 2 is 1 upon root 3, x 2 is 1 upon root 3. So, this gives me 1 upon 3 root 3 minus 1 upon root 3 plus root 3 by 9. So, this is root 3 by 9, this is root 3 by 9. So, I can write this as 2 root 3 by 9 minus root 3 by 3. So, this gives you minus root 3 by 9. Now, you can see that the error epsilon 0 is plus root 3 by 9, epsilon at 1 by root 3 is minus 1 root 3 by 9 and epsilon at 1 is root 3 by 9. The errors of equal magnitude and they are alternating in sign. So, the maximum error is equal to minimum error, and we have got this as the best approximation in the uniform sense, that is the Chebyshev polynomial approximation. Now, we would like to generalize the result for any polynomial. So, let us generalize this result and we call this result as the Chebyshev equi-oscillation theorem. So, we call this as Chebyshev equi-oscillation theorem. This is the basis of the uniform approximation for a general polynomial. Now, we are given a continuous function. So, let us start with a continuous function. Let f x be continuous on a given interval a b. Then we have an approximation. So, let p n x be an approximation. Let p n x be an approximation. That means, we are writing p n x as a polynomial c naught plus c 1 x, so on c n x to the power of n. Then we define the error, define epsilon x is equal to epsilon n x, we can now put is f x minus p n x, and the maximum value will denote by capital E. So, epsilon n x f x is equal to maximum of this error in the given interval this. These are all the definitions that we have used earlier. Now, we state the equi-oscillation theorem out of this. We will say then there exists n plus 2 points, there exists n plus 2 points we will take a is equal to x naught less than x 1 less than x 2 x n plus 1 is equal to b. We are considering x naught to x n plus 1 n plus 2 points, the first point is a, the last point is equal to b. Now, there exists n points such that one error at x I is plus minus E n, that is your the E n is the maximum magnitude of the error. Therefore, error at this will have either plus or minus sign of E n. So, and this is for I is equal to 0, 1 to n plus 1. That means, this actually is telling us that errors at all points are of same magnitude. So, this is stating that errors at all points are of same magnitude. Secondly, error at x I is equal to minus error at x I plus 1, starting from I is equal to 0, 1, so on n. Epsilon at x 0 is equal to minus epsilon 1, and lastly error at x n is equal to minus error at x n plus 1, and this states that the errors alternate in sign. Now, this second part would therefore give us the application of Rolle's theorem can be applied using this. So, we can now state that this implies application of Rolle's theorem gives that derivative at x I is equal to 0, I is equal to 1, 2, 3 n. There are a total of n plus 2 points, and you have got errors at all these points are same in magnitude, and hence the Rolle's theorem can be applied, and you will have n intermediate points at which the errors will be equal to 0. Now, we can say that 1 gives us n plus 1 equations, these are n plus 1 equations, and this gives us n equations. Therefore, n gives us 1 gives us n plus 1 equations, and 2 gives us n equations. So, that we have a total of 2 n plus 1 equations. Now, what are the unknowns that we have here? The unknowns that we have are x 1, x 2, the first point and the last point are known to us. Therefore, x 1, x 2, x n are the points in the middle, and then we have the parameters in the polynomial c 0, c 1, c 2, c n, and these are 2 n plus 1 unknowns. Therefore, we have 2 n plus 1 equations in 2 n plus 1 unknowns, and these are of course nonlinear equations, and we have way of, as we have shown earlier, there is a way of solving them. We can solve this and then get the uniform approximation, and finally we can determine, using any point x naught or the first or the last point, we can finally determine what is the maximum value of this and then take that as our uniform error. Now let us take an example for a quadratic polynomial. Let us do the same example for the quadratic approximation. So let us take it as obtain the best uniform approximation of second degree for f x is equal to, I will take the same example x cubed on 0 1. Now I need to consider a polynomial of degree 2, therefore I will consider p 2 x as my polynomial c naught plus c 1 x plus c 2 x squared, and error is equal to x cubed minus c naught plus c 1 x plus c 2 x squared. Now given a polynomial, the number of points that should be chosen is given over here. So we need to choose a total of n plus 2 points given a polynomial. So given a polynomial of degree 2, so I need to have n plus 2, that is 4 points. Therefore we say choose 4 points. The first and last we will take as this 0, then we will take x 2, we will take x 3 and x 4, x naught, x 1, x 2, x 3, x 4. Now let us first write down all the equations which we should get here, that is epsilon 0 is equal to minus epsilon at x 2, epsilon at x 2 is equal to minus epsilon at x 3, epsilon at x 3 is minus epsilon at x 1. Then we have the derivatives, epsilon dash at x 2 is equal to 0, epsilon dash at x 3 is equal to 0. Now while solving this system, as I mentioned earlier, we shall first solve the which one that combines the first and the last, because then there is no parameter. So if you look at that one, what that equation would be, epsilon 0 is minus epsilon x 2. So substitute a minus sign here, that is plus epsilon x 3, and plus epsilon 3 is minus epsilon 1, minus epsilon 1. So that particular equation which you are looking for, which simplifies the first equation, is we start with epsilon 0 is minus epsilon 1, and that will give me, it will have only one parameter, therefore I can solve that particular equation immediately and then substitute backwards in these equations to get the values of the other parameters. Now let us first of all write down what these values are. So you will have here, let us write down again, epsilon 0 is minus epsilon x 2. Now this gives us, I am substituting in this particular equation, therefore I will have simply minus c 0, that is the left hand side, and the right hand side is x 2 cubed c naught plus c 1 x 2 c 2 x 2 square. That is our first equation. So let us again number it as 1 2 3 here. Now the second equation is epsilon x 2 is minus epsilon x 3. So that is your x 2 cubed minus c naught c 1 x 2 c 2 x 2 squared. This is at x 3 we will have x 3 cubed minus c naught c 1 x 2 c 1 x 3 C2 x3 square, and the third equation reads epsilon x3 is epsilon 1, that is x2 cubed C naught plus C1 x3 C2 x3 squared is minus of, substitute x is equal to 1, I will get here 1 minus C naught plus C1 plus C2. Now, let us write down the last two equations that we have here, that is the derivatives at x2 and derivative at x3 is equal to 0. So, if I now differentiate this epsilon x here, I would get here 3 x2 square minus C1 plus twice C2 x2 is equal to 0. I differentiated this, C1 plus twice C2 x is equal to 0, and similarly 3 x3 squared minus C1 plus twice C2 x3 is equal to 0. So, I have got this equation 2, this is 3, 4 and 5. I would like to use this particular equation which gives me a solution immediately. Epsilon 0 is equal to minus epsilon 1. So, if I do that, that is epsilon 0 is minus C 0, epsilon 0 is minus 0 and minus epsilon 1 is here. So, I can lift it as it is. So, this will be equal to minus 1 plus C naught plus C1 plus C2. Right, this gives me 2 C naught plus C1 plus C1 plus C2 is equal to 1. Now, I think I will leave this as an exercise for you to complete the problem. I will give you the solution of this problem. You can verify the values of C naught, C1, C2 and so on. So, I would give the values of x2 is 1 by 4, x3 is equal to 3 by 4, C naught is 1 by 32, C1 is minus 9 by 16 and C2 is 3 by 2. Therefore, our best uniform approximation is 1 upon 32 minus 9 by 16 x plus 3 by 2 x square. So, this is the best uniform approximation. And we can actually find out what the error is. We can find out the error that will be equal at any of these points, particularly with respect to at the first point we can find out what will be the maximum error, and that will give you the maximum error in this equation. Now, we have earlier talked about least square approximation, and in the least square approximations we wanted to use the orthogonal polynomials which will give the values of the coefficients immediately as a ratio of two integrals if it is a continuous function, or the ratio of sums of the some wxi into the orthogonal polynomials. And we would now like to define the two polynomials which can be used in least square approximation, as well as we shall be using in the next topic, that is in numerical integration also. So, let us define these polynomials, orthogonal polynomials, which you must have done in your earlier course also, but let us just briefly revise what is those polynomials and what are the properties of those polynomials which makes them very powerful. Of all of them, the Chebyshev polynomials is supposed to be the best, and we will see why Chebyshev polynomial is the best. So, let us just briefly describe these polynomials. The Legendre polynomials. Now, we are really talking of Legendre polynomials of first kind, because the polynomials, Legendre polynomials that we talk of normally is only the polynomials of the first kind, that is the polynomials p and x. the first polynomial is 1, p1 of x is equal to x, p2 x is equal to half 3 x squared minus 1 and so on. I can generate all of them through a recurrence relation. If once I know 2 of them, it is sufficient for me. I can now write down the recurrence relation and get any Legendre polynomial I want from here. So, the recurrence relation for this is this. N plus 1 p n plus 1 x is equal to 2 n plus 1 x p n x minus n p n minus 1 x. Therefore, when once I know p 0 p 1, I can now generate from here by taking n is equal to 1, I can get my p 2, I can get my p 3, all of them. So, I can generate all the polynomials whichever polynomial I want using this reconciliation. Now, these Legendre polynomials are obtained as the solutions of a differential equation. They all belong to the problem called the Sturm-Liouville problem, in which the coefficients can be taken differently, and the solutions of these differential equations of the Sturm-Liouville problem gives rise to these orthogonal polynomials. That is one class of problems which produces a large number of orthogonal polynomials, and these polynomials are defined in the interval. Let us write it here itself. They are defined in the interval minus 1 to 1. They are defined over the interval minus 1 to 1. Now, the differential equation governing this is this. One minus x squared y double dashed minus 2 x y dashed plus n into n plus 1 of y is equal to 0. This is also called the Legendre's differential equation. This is called the Legendre differential equation. I can write down the series solution for this differential equation. You have done the series solution of differential equations. So, I write the series solutions of the differential equations, and the one of the solutions would give me the orthogonal polynomial, that is Legendre polynomials of first kind, with a suitable coefficient that has been prefixed to it, and that coefficient is determined with some property that p n of 1 is equal to 1. You can see that p n of 1 is 1 always. So, using that, it is one can determine what will be the coefficient that is there. The orthogonal property is the one that we have been using earlier. The orthogonal property is with the weight function 1 here, minus 1 to 1 p m x p n x dx is equal to 0 for m not equal to n, 2 upon 2 n plus 1 for m is equal to n, and in this case the weight function w x is equal to 1. Now, this is one of the set of polynomials that we shall use. The Legendre polynomials of second kind are not used because they are not of great use. It is only the Legendre polynomials of first kind are of use. Now, let us define the Chebyshev polynomials. Here again we shall be considering only Chebyshev polynomials of first kind. These polynomials are denoted by T n of x. Interestingly, even though it is a polynomial, it can be written in a nice closed form in the trigonometric function form as cos n cos inverse of x, or simply cos of n theta cos n theta. That means, we have set cos inverse of x is equal to theta, or x is equal to cos of theta. So, if I set cos inverse x is theta, I would get x is equal to cos theta, and therefore, they are all defined on minus 1 to 1, defined on minus 1 to 1, the same as in the Legendre polynomial. the differential equation that governs this is 1 minus x squared y double dashed minus x y dashed plus n square y is equal to 0. This is the Chebyshev differential equation. Now, I can set n is equal to 0, 1, 2 here and then get the values of the Chebyshev polynomials of first kind. Again T naught of x is 1, T 1 of x is equal to x, the first two polynomials are the same. T 2 x is equal to 2 x squared minus 1. In both the Legendre polynomials as well as Chebyshev polynomials, we can write x in terms of polynomials also. So, I can write down reverse relations also, that is 1 can be written as T naught, x can be written as T 1, then I can solve for x square from here, 2 x squared is equal to T 2 plus 1, but 1 is T naught. So, I can write this as T 2 plus T naught, and therefore, I can write down x squared as half of T naught plus T 2. Therefore, it is possible for me to write down express the polynomials in terms of the Chebyshev polynomials starting with that degree, that is T 2 and lower ones, and here since it is even, so it will contain only T 2 plus T naught. If it is an odd power, it will contain your odd Chebyshev polynomials, degree Chebyshev polynomial, that is T 1, T 3, x cubed will be in terms of T 3 and T 1. Now, again I can generate all of them through the recurrence relation. The recurrence relation for the Chebyshev polynomials are T n plus 1 of x is 2 x T n x minus T n minus 1 x. Now, I can expand this cos n cos inverse x to determine what is the leading coefficient for me in T n x, because that is something very important and useful for us. That T n x is equal to, I can show that this is equal to 2 n minus 1 x to the power of n plus lower degree terms. So, that the leading coefficient of T n x is 2 to the power of n minus 1. Now, I can define from here what is a monic Chebyshev polynomial, that is a polynomial with leading coefficient as 1. So, if I define divide T n x by 2 n minus 1, then I will have a monic Chebyshev polynomial. So, I can write this as 1 upon 2 to the power of n minus 1 T n x is equal to x to the power of n plus so on. So, this defines a monic Chebyshev polynomial of degree n. Now, before I mention where I am going to use it in a moment, let us just also write down what is the orthogonal property. Orthogonal property. The weight function for Chebyshev polynomials is 1 upon under root 1 minus x squared. So, the weight function for Chebyshev polynomial is not a constant, but it is this particular form. Therefore, my integral minus 1 to 1 w x into T m x T n x. So, we will now substitute for that T m x T n x into w x, that is 1 minus x squared under root dx. This is equal to 0 for m not equal to n. If I put m is equal to n, I will get pi by 2, m is equal to n not equal to 0, but this will be equal to pi if it is equal to 0. Now, the most important thing here is that magnitude of t n x. Now, what is the definition of t n x? It is a cosine function. It is a cosine function. Therefore, its magnitude is going to be less than 1 always. Therefore, magnitude of t n x is always less than or equal to 1. Now, this is something very useful for us, that the magnitude of any Chebyshev polynomial is less than or equal to 1. Now, as I was saying, I wanted to use this particular property. What is so great about this one? So, if I can you just denote this by tilde, t tilde x tilde t n. Now, I consider now any polynomial with leading coefficient 1. P n x is any monic polynomial. That means leading coefficient is 1, that is, it is of the form x to the power of n plus some b 1 x to the power of n minus 1 and so on. Therefore, the leading coefficient is equal to 1. Now, if I consider the monic Chebyshev polynomial and arbitrary monic polynomial on the interval -1 to 1 and consider its magnitude, then the monic Chebyshev polynomial is the smallest in magnitude of all the polynomials on -1 to 1. There is no polynomial whose magnitude will be less than this particular Chebyshev polynomial. So, the property that we want to show is the maximum over -x to 1 of t this, that is your monic Chebyshev polynomial, is less than or equal to -1 to 1 this of p n x. This is the property which makes Chebyshev polynomials as a rarest of the orthogonal polynomials, because you cannot find any polynomial whose magnitude will be less than the polynomial. Therefore, in all the approximations we would prefer to use Chebyshev polynomials because its error is going to be smallest, and this property is called the minimax property of Chebyshev polynomials. That is why you will find that when we are applying in any particular problem, even though Legendre polynomials can also be used, Chebyshev polynomials can also be used. Chebyshev polynomials are preferred because of this particular property. Okay, we would stop.